December 1944. Inside a dimly lit hangar on the outskirts of Rechlin, the air was heavy with the smell of oil, metal, and a creeping, unspoken defeat. This was the Erprobungsstelle Rechlin, the central test facility of the Luftwaffe, the once unassailable German Air Force. Now, Germany was still fighting, but every man in that room, engineer, mechanic, and officer alike, sensed the inevitable outcome. The war was no longer a question of if, but when. Under the harsh, isolated glare of a single floodlight stood a massive engine crate. Its wooden planks were scarred, the stencilings faded but still legible. Pratt Whitney Aircraft, R-2800. This was not a trophy captured in the triumphant skies of 1940. It had been salvaged, prized from the twisted, burned wreckage of an American P-47 Thunderbolt. The aircraft, serial number 4222490, nicknamed Beetle by its former pilot, had been shot down over northern France. The fuselage was a mangled ruin, but the engine, this enormous 18-cylinder twin-row radial beast, had somehow survived the impact and fire largely intact. Technicians from the Luftwaffe's experimental division gathered around it. They were priests about to open a relic, but one from a faith they did not understand. They whispered among themselves. "So this is what powers their flying milk bottles?" one muttered, using the mocking nickname German pilots had given the P-47. To the artisans of Messerschmitt and Focke-Wulf, the American fighter was a brute. It was heavy, clumsy, a machine that seemed to defy every hard-won principle of elegant, high-performance engineering. Yet this flying anvil, this pregnant cow, was slaughtering them. No one understood how. How could a machine this large, this ponderous, climb to altitudes where their own fighters gasped for breath? How could it absorb such catastrophic punishment, dozens of cannon hits, and still carry its pilot home? The Luftwaffe High Command, desperate for an answer to the waves of American bombers now leveling their cities, wanted answers. The order from Berlin was clear, delivered with a frantic urgency. Disassemble the captured engine. Analyze every component. Find the secret. Crowbars screeched as the crate was pried open. The mechanics stepped back as the floodlight hit the metal. It was a solid mass of alloy and power. The double row of cylinders formed a perfect gleaming circle under a layer of grime. A technical officer named Oberleutnant Hans Schultz ran his gloved hand across the casing, his fingers tracing the embossed words, "Double Wasp." Schultz had spent his life around German engines. He knew the intricate, handcrafted soul of the BMW 801, the engine that powered Germany's own formidable FW-190. He understood the delicate, high-strung power of the Daimler-Benz 605. But this was alien. It was obscene in its sheer scale. The cooling fins were thicker. The bolts looked oddly, almost crudely oversized. The exhaust manifold was arranged in a complex pattern none of them recognized. "Too heavy," someone said dismissively. "The Americans overbuild everything, a waste of material." Schultz didn't reply. He had heard that sentiment before. It was the standard refrain in a nation that had built its war machine on scarcity, on genius honed by limitation. But as he looked at the American engine, a cold thought settled in his mind. Overbuilt, sometimes, just meant built to last. For a moment, the hangar was silent, save for the clink of wrenches and the hiss of kerosene lamps. Outside, snow drifted across the airfield, muffling the distant, rhythmic thunder of artillery from the Western Front. Inside, Hans Schultz and his team began the slow, ritualistic dismantling of a masterpiece they did not yet understand. The winter of 1944 had found the Luftwaffe's Technical Bureau drowning in bad news. The problems were no longer theoretical, they were catastrophic. Squadrons once filled with hardened veterans, aces who had fought over Spain, France, and Britain, were now led by boys barely old enough to shave. Fuel stocks were so heavily rationed that training flights had been reduced to 30 minutes a week, a pathetic allowance to prepare a pilot for the meat grinder over the Reich. And yet, from the Western Front to the skies over Berlin itself, this strange American fighter kept appearing. It was bigger, heavier, and louder than anything the Germans had ever seen. The men in the intelligence office at Adlershof called it the Thunderbolt. At first, the pilot reports were dismissed as exaggerated, even absurd. "We hit it dozens of times," one frantic transmission read, "and it kept flying." Another pilot, a veteran from the elite Jagdgeschwader 26, claimed a P-47 had dived straight through his entire formation of F-190s, its guns roaring, and vanished into the clouds below before anyone could even react. The High Command dismissed these as excuses from pilots losing their nerve. No airplane that large could fight like that. Then, the wreckage started arriving. Crashed Thunderbolts were being recovered across occupied Europe, and the more the engineers examined them, the less sense they made. Their engines were enormous. Their fuselages were not built, they were vaulted. German technicians noted with a mix of horror and admiration that the airframes were constructed like a fortress, built around a massive central keel. Redundant control cables were routed through different sections, ensuring a single lucky hit could not sever them all. Even a machine gun burst that would have torn a Messerschmitt in two barely seemed to leave scratches on the Americans. The pilots who once mocked the flying milk bottle began to curse its name. One veteran ace, Heinz Baer, summed it up bitterly. "The P-47 can absorb an astounding amount of lead. They have to be handled very carefully." German technical staff, with their typical black humor, had their own names for it: Betonflugzeug, concrete aircraft, and der amerikanische Hammer, the American hammer. What truly alarmed the engineers at Rechlin, however, wasn't just the Thunderbolt's toughness, it was its altitude. On the Eastern Front, the Luftwaffe had dominated with the FW-190A, a brilliant low to medium altitude dogfighter. But over Western Europe, the rules had changed. P-47s were climbing to 30,000 feet, even 35,000, well above the operational ceiling of most German interceptors. They would attack from above, diving with devastating speed that no German fighter could match. German tactical instructions explicitly warned pilots not to dive away from a P-47. It was suicide. The American fighter would simply accelerate beyond their maximum speed and tear them apart. The culprit was the engine, the Pratt Whitney R-2800 double Wasp. At altitude, where the air was thin and temperatures could freeze metal solid, this engine somehow maintained full power. By comparison, the brilliant BMW 801, with its mechanical supercharger, gasped for breath above 25,000 feet, unable to feed enough air to its cylinders. The Luftwaffe's technical office launched a formal investigation. They needed to know how the Americans had done it. Orders were sent to the Rechlin Test Center. Acquire and dissect any intact R-2800 recovered from wreckage. The hope was simple, if desperate. Find its secrets, copy them, and restore parity to the skies. But by then, Germany's industrial reality was collapsing. Allied bombers, often escorted by these very P-47s, had leveled the ball-bearing factories in Schweinfurt. Aluminum plants in Norway and fuel refineries in Ploesti were burning. Even if Rechlin discovered the secret, replicating it was another matter entirely. Still, the investigation proceeded. Pride demanded it. To understand what made the Americans different, one must first understand how the Germans thought about machines. To the engineers of Daimler-Benz and BMW, an aircraft engine was a masterpiece. It was a creation to be tuned, polished, and perfected by craftsmen who believed that beauty and precision were inseparable. Each component was hand-fitted, each bearing was inspected by eye. The result was performance unmatched in the world, when the materials were pure and the hand steady. But it was a system built for perfection, not for total war. Dr. Ernst Haenkel, a German aircraft designer, confided to his associates, "We are artisans building aircraft. They are industrialists manufacturing them. We cannot compete with mathematics." In America, the philosophy was the opposite. The R-2800 wasn't designed for artisans. It was designed for assembly lines. Every bolt, every thread, every gasket was standardized, so that thousands of factories across the country could build the same engine with identical tolerances. Instead of handcrafting, they used machines so precise that the difference between two pistons was measured in microns. Where Germany built art, America built quantity. And quantity, in the harsh, unforgiving mathematics of war, eventually becomes a quality all its own. By early 1944, this difference had become a strategic chasm. German pilots were fighting on two fronts with engines that required hours of maintenance after every single sortie. American engines, by contrast, could fly dozens of missions with minimal servicing. The R-2800, German intelligence noted, could reliably run for over 400 hours between major overhauls. The BMW 801, if it was lucky, might fail after 100 combat hours. In the skies over Europe, that difference was life and death. A single factory in East Hartford, Connecticut, produced more R-2800 engines in a month than Germany could build high-performance engines in a season. The total production of just this one engine model, over 125,000 units by the war's end, would exceed Germany's entire combat aircraft engine production for the whole war. For the Luftwaffe, the captured P-47 engine wasn't just a technical curiosity. It was a question of survival. That was why, when the wreck of Beetle fell near Caen and its engine was found largely intact, it was shipped across Europe under heavy guard. The crate that arrived at Rechlin in December was more than just scrap metal. It was a symbol of everything Germany was losing: altitude, speed, and time. In a report to the Ministry of Armaments, a senior engineer had written, "We believe the Americans have solved the altitude problem through wasteful use of materials and fuel." He meant it as a criticism. But the truth was darker. The Americans could afford to be wasteful. They had more aluminum, more fuel, more factories, and more men. The Thunderbolt was not a miracle of engineering. It was the logical, brutal result of an economy that dwarfed its enemy. Still, the Germans couldn't resist one final act of defiance. They would open the engine. They would study it. And they would prove that they could understand, even if they could no longer replicate. Oberleutnant Hans Schultz and his team were selected for the job. They knew radial engines better than anyone in the division. Before the first bolt was turned, the chief engineer of the facility gave a short, terse speech. "Gentlemen," he said, his voice flat, "this engine is not magic. It is metal and mathematics, and both can be conquered." The men nodded, their faces grim in the cold. None of them knew that within hours, their certainty, the very foundation of their engineering pride, would begin to crumble. What they would find inside the double Wasp wasn't just superior engineering. It was an entire philosophy of war made tangible, one that valued reliability over elegance and production over perfection. The hangar was silent except for the sound of tools. Each turn of a wrench echoed in the cavernous space like a heartbeat. Oberleutnant Hans Schultz crouched beside the massive R-2800, his gloved fingers tracing the bolts that held the cowling in place. The Americans had designed this engine like a fortress. Every joint was sealed, every connection reinforced. When the first layer of metal finally came free, a hiss of stale oil and burned residue escaped into the air. It was the ghost of its last flight over France. The men leaned closer under the floodlights. The engine's anatomy gleamed like a dark sculpture. To a German mechanic's eye, the construction was bewildering. The BMW 800 that powered the FW-190 was a marvel of compact integration. It was dense, elegant, a triumph of efficiency. This American engine was its opposite. It was a sprawling, oversized brute. The cylinders were thick-walled, the clamps heavy, the systems redundant. "It's absurd," muttered one technician, wiping grease from his hands. "They've built it as if weight doesn't matter." He wasn't wrong. The R-2800 weighed nearly a ton, significantly more than its German counterpart. But Schultz was beginning to sense something the others hadn't yet seen. The parts didn't just look heavy, they looked unbreakable. This was the first revelation. The P-47, they already knew, was notoriously rugged. Reports from the front told of Thunderbolts returning to base with 3, 4, or even 5 of their 18 cylinders completely destroyed. The radial engine, being air-cooled, provided an inherent redundancy. Losing a cylinder was a problem, but it wasn't a death sentence. For a German liquid-cooled engine like the DB605 in a Messerschmitt, a single hit to the cooling system was fatal. The engine would seize in minutes. The R-2800, with its massive, robust crankcase, could sustain direct hits from 20mm cannon fire and keep running. Schultz moved to the front of the engine and began the process of removing one of the cylinder heads. He and his team expected to find competence. They did not expect to find perfection. The machining was immaculate. Every thread was perfect. Each gasket fit so tightly it seemed fused to the metal. He called over the chief engineer. Together, they examined the finish under a magnifying glass. There were no burrs, no imperfections, no tool chatter. It was the kind of precision one would expect from a watchmaker, not from an engine built by the tens of thousands. "Look at the uniformity," Schultz whispered. "Every component, it could be swapped between engines, and it would still fit." That was the second revelation, and it was more profound than the first. German engines were hand-fitted. They were tuned by skilled craftsmen who adjusted and lapped parts until they worked together in perfect harmony. Each one was unique, a bespoke piece of art. This American engine was different. It was interchangeable. It was a product of exact tolerances and machine perfection. One of the most senior engineers present, a man on loan from the Blohm & Voss aeromaker, was inspecting the crankcase. He had been silent for an hour. Now he motioned Schultz over. He pointed to the seam where the two halves of the massive crankcase joined. "There is no sealing gasket," he said, his voice barely audible. Schultz frowned, confused. "What?" "There is no gasket," the engineer repeated. "The lapping of the two halves, it is machined with such great precision that it does not require one, and it does not leak oil." The other mechanics stopped their work. They understood the impossibility of what he was saying. To machine two massive, complex pieces of metal with such perfect flatness that they could be joined under pressure and remain oil-tight was a feat of manufacturing that boggled the mind. To do it on one engine was a master's work. To do it on thousands? The Blohm & Voss engineer looked up at Schultz, his face pale. "Oberleutnant," he said quietly, "if the Americans can mass-produce this, the war is already lost." Schultz realized that behind this engine wasn't just engineering skill, but a production philosophy his country had never mastered. He looked at a simple spark plug he'd removed. It was marked Champion, Toledo, Ohio. Every one of the 36 plugs was identical. It was, as Schultz would later write in his report, a kind of genius. Then came the third and most devastating revelation. As the team dismantled the rear housing, they uncovered a massive, circular assembly unlike anything they had ever seen on a piston engine. The chief engineer frowned. "This can't be right," he murmured. The component was a turbine, huge and complex, connected to the exhaust ports by a web of polished steel ducts. When the Americans said turbo-supercharger, the Germans had imagined a small mechanical compressor, similar to their own. This was something else entirely. This was a gas-driven turbine harnessing the waste heat from the exhaust, heat reaching 1,500 degrees Fahrenheit, to spin a rotor at over 20,000 revolutions per minute, forcing massive amounts of compressed air into the cylinders. Schultz carefully removed the casing. Inside, a wheel of blades glittered under the lamplight. He touched the metal and drew his hand back. The alloy was strange. It was smooth, hard, and faintly iridescent. They tested it with a file. The hardened teeth barely scratched the surface. One of the metallurgists whispered, "This is not steel." He was right. It was a nickel-chromium superalloy, possibly Inconel. It was a metal that could survive temperatures above 700 degrees Celsius without deforming, without shattering under the colossal centrifugal forces. Germany had experimented with similar metals, but never on this scale. Nickel was scarce, a strategic material Germany no longer possessed. Chromium was reserved for armor plating. The Americans, it seemed, had built entire, complex systems out of it. The realization spread slowly through the group. This was the secret. This was how the P-47 could climb to 30,000 feet and maintain full power. The R-2800's turbo system allowed it to recreate sea-level air density even where the air was as thin as mountain frost. This was what Oberleutnant Schultz would later describe in his report as the Americans having tamed the atmosphere itself. The Germans could see the logic, but they could not comprehend the practicality. To build just one of these, the chief engineer said quietly, we would need half the resources of the Reich, and the Americans were installing it as standard equipment. They moved on, their earlier confidence replaced by a grim, methodical silence. They examined the cooling system. Here, too, the Americans had done something different. Instead of relying solely on airflow, they had built a labyrinth of baffles, oil lines, and intercoolers that distributed heat evenly. The BMW 801 required constant, careful monitoring to avoid overheating. The R-2800, with its automatic regulators, could run at full power for hours without burning a valve. When they opened the magneto housing, Schultz discovered yet another surprise. The ignition system was double redundant. 2 spark plugs per cylinder. 2 complete magnetos, twin distributors. If one entire system failed, the other would keep the engine running. In the Luftwaffe, where every gram was counted, such redundancy was considered unnecessary weight. Here, it was standard practice. They build like they don't care about limits, a mechanic muttered. They don't have to, another replied. By dawn, the R-2800 lay disassembled across 4 workbenches, its guts exposed like the anatomy of some extinct, iron-willed creature. The Germans gathered around the pieces in silence. For years, they had believed in their own superiority. Better pilots, better tactics, better technology. But what they saw on those tables forced them to confront another, more terrible truth. The Americans had mastered something more powerful than innovation. They had mastered scale. Every component of the R-2800 told them that behind each Thunderbolt stood not a single genius engineer, but an army of machines, workers, and factories. It was an industrial ecosystem built to outlast any enemy. Schultz picked up one of the pistons and held it to the light. The alloy was flawless, the surface polished like glass. He turned it over in his palm, feeling its weight. In another life, it could have been art. He thought about the pilots who had flown this engine, the young Americans who took to the air, knowing that somewhere back home 1,000 more engines waited to replace theirs. That was a luxury no German pilot could imagine. He set the piston down carefully and spoke in a voice barely above a whisper. "We can copy the shape," he said, "but we cannot copy the soul." No one disagreed. Outside, the gray light of morning spilled through the hangar doors. The war was still raging, but in that cold, greasy silence, the men around the table understood what the front lines had not yet realized. The outcome was already written in metal. By the time the sun rose over Rechlin, the men in the hangar were still staring at the rows of components. The R-2800 had been opened, measured, and studied, but the feeling it left behind was not triumph. It was resignation. They had expected a clever trick, a secret patent, perhaps a new valve design. What they found instead was something far more intimidating. The sheer, brutal perfection of repetition. Every part, from the smallest bolt to the largest turbine blade, was marked with serial codes. These codes traced back to factories across the United States. Schultz held a connecting rod in his hand, its surface stamped with a neat set of numbers and letters. East Hartford, 1943, Lot 128. To him, it was both a signature and a taunt. Each marking told the same story. This was not the product of a single genius or a small, dedicated workshop. It was the output of a vast industrial organism that stretched from Detroit to Connecticut to Los Angeles. Later that week, a detailed intelligence report from Berlin arrived at Rechlin. It included a set of statistics captured through intelligence channels. Schultz read them in silence. The United States was producing more than 850 aircraft engines per week. The Pratt Whitney plant in East Hartford, running 24 hours a day, was completing 1,000 R-2800 engines every week. Over 15,000 Thunderbolts had already rolled off assembly lines by that winter, and more were coming. Corsairs, Hellcats, Marauders, all using the same R-28 heart. Germany, by contrast, was struggling to build 200 high-performance fighter engines a month. Most of them were assembled in underground factories, bombed so often that workers had to finish parts by candlelight. To an engineer, numbers tell their own kind of story. They are the language of possibility and of doom. When Schultz compared the figures, he realized that even if Germany somehow duplicated the R-2800 exactly, they could never match the speed or scale at which America built them. America had made precision into a process. Germany had made it an art. One could be multiplied 1,000 times. The other could not. Inside the hangar, Schultz began to disassemble the turbo housing for metallurgical samples. The lab analysis confirmed his suspicions. The turbine blades, the ones that glittered under the lamplight, contained 22% nickel and 14% chromium, metals Germany no longer possessed in any meaningful quantity. In 1943, the Reich's stockpiles of nickel had fallen below half of what was needed for basic aircraft production. Chromium came mostly from mines in the Balkans, now under Allied control. Even if they had the blueprints, the materials themselves were beyond reach. A metallurgist handed Schultz the analysis sheet. "If we tried to cast this alloy with our current supply," he said quietly, "it would shatter before it ever reached operating temperature." Schultz nodded, the cold realization sinking deeper. "Then it isn't just the engine we can't copy," he said. "It's the civilization that built it." Across the Atlantic, that civilization was operating at full throttle. At night, the East Hartford factory glowed like a furnace, powered by electricity drawn from rivers and coal reserves untouched by enemy bombs. Precision lathes shaped steel to tolerances measured in microns. Entire neighborhoods existed just to house the workers who built the engines, like the one lying in pieces in Schultz's hangar. The Luftwaffe's intelligence department compiled more comparisons. The average American engine mechanic had access to over 300 specialized tools. In Germany, shortages meant many workshops had to share a single torque wrench among several teams. The Americans used alloys containing cobalt and molybdenum. The Reich relied on recycled metals stripped from damaged aircraft. The contrast was not just in numbers. It was in philosophy. German engineers believed that perfection required the human touch, that every machine carried the fingerprint of its maker. The Americans believed that perfection came from eliminating those fingerprints altogether. To them, reliability wasn't art, it was arithmetic. The irony was cruel. Schultz knew that a single R-2800 engine could outlast 3 or even 4 BMW 801s in combat hours. While the Luftwaffe's fighters required major servicing after perhaps 100 hours of flight, the Thunderbolt's engine could run more than 400 hours before overhaul. In the skies over Europe, that difference meant life and death. He turned back to the table and studied the magneto housing again. The Germans had always dismissed redundancy as wasteful, extra weight for pilots to carry. But the Americans had built redundancy into every system, accepting inefficiency to guarantee endurance. It was a logic born not of desperation, but of abundance. Oberleutnant Schultz noted in his draft that the Thunderbolt reflects a design philosophy rooted not in scarcity, but in abundance. That afternoon, Schultz wrote his formal report. He listed the technical observations in precise, sterile language. Excellent alloy quality, remarkable thermal tolerance, unusual reliability at high manifold pressure. But in the final paragraph, he allowed himself a rare moment of stark honesty. This engine represents a philosophy we cannot match. Its strength lies not in innovation, but in the industrial depth of its nation. It is a weapon of production as much of flight. When the report reached Berlin, it was summarized in 2 sentences for the Air Ministry. The American R-2800 is unnecessarily heavy but highly robust. Its power is derived from wasteful design and excessive material use. Bureaucrats underlined the phrase wasteful design, using it to justify the continued focus on lighter, more efficient German engines. None of them understood. None of them saw that this wastefulness was the entire secret. It was the secret to survival. Weeks later, a second R-2800 arrived from another wreck. The engineers unpacked it with less enthusiasm. They already knew what they would find. Still, they repeated the measurements, the weighing, the analysis. Each time, the results were the same: precision, power, and reliability produced at a scale Germany could only dream of. Schultz began to keep his own private notes, scribbled in the margins of his blueprints. "Every component is built for forgiveness," he wrote. "They expect it to fail, and so they make sure it can." That single line captured the difference between the two empires. Germany designed to avoid failure. America designed to survive it. When he finished his final inspection that evening, he stood by the open hangar door and watched the snow drift across the runway. The war was now being lost in ways no pilot could see. It was being lost from shortages, from exhaustion, and from an enemy whose factories outproduced his own by 20 to 1. The R-2800 wasn't a secret weapon. It was the proof. It was the proof that technology had become the servant of economy, and economy had become destiny. While Schultz and his team were dissecting the R-2800 at Rechlin, another German, Reich Minister of Armaments Albert Speer, was staring at a different set of figures and coming to the same terrifying conclusion. Speer, the architect of Germany's industrial miracle, had just received intelligence reports on American production for 1944. The numbers were so vast, he initially assumed his intelligence staff had made a decimal error. They had not. The United States, his report stated, was on track to manufacture approximately 96,000 aircraft in 1944. Germany, even at the peak of Speer's frantic efforts, was on track to produce 39,870. The United States alone was outproducing Germany by nearly 2.5 to 1. When Allied production, including British and Soviet output, was combined, the advantage exceeded 5-1. Speer reportedly told Hitler at a conference, "The Americans produce in 1 month what we produce in a year." When he presented photographic evidence of the massive Willow Run facility, which applied Henry Ford's automotive techniques to produce one B-24 Liberator bomber every 63 minutes, Hitler flew into a rage. He declared it propaganda. "The Americans wish us to believe these fantasies. No nation can produce aircraft like automobiles." He insisted the reports were Jewish lies spread by Roosevelt. But Speer knew the truth. He submitted a formal memorandum to Hitler in March 1944, a document of pure despair. He stated that the enemy's production capacity in aircraft manufacture exceeds our capacity by a factor of 4-1 in fighters and 6-1 in heavy bombers, and that this disparity was increasing monthly. Speer privately met with Field Marshal Erhard Milch, the state secretary in the aviation ministry. "The numbers are correct, aren't they?" Milch asked, already knowing the answer. "I believe they are conservative," Speer replied. Milch paused, the blood draining from his face. Then he said, "We have already lost." It was Milch who had reviewed the technical brief on the captured R-2800 engine from Rechlin. His assistant summarized it cautiously. "Their design prioritizes reliability and mass manufacture, not elegance." Milch frowned. "So it's crude?" "Yes, sir," came the reply. "But it works." Milch closed the folder, his voice sharp with the pride that was now Germany's only remaining strategic asset. "We will not copy crude." That sentence sealed more than a dozen decisions that would haunt Germany's air war until the end. The R-2800's lessons were clear, but they were lessons the German system could not and would not accept. The Reich's engineers believed that technical superiority equaled victory. They saw the war as a contest of invention, not of endurance. In America, the philosophy was reversed. Build simple, build strong, and build so many that losing 100 meant nothing. That difference now defined the skies over Europe. As 1944 unfolded, the Thunderbolt squadrons became a force the Luftwaffe couldn't counter. With its turbo-supercharged engine, the P-47 could escort bombers deep into Germany, dive at 500 miles per hour, and climb above any piston aircraft the Reich possessed. Its pilots called it the Jug, short for Juggernaut, and the name fit perfectly. German fighters that tried to intercept the B-17s found themselves hunted by these blunt-nosed monsters that simply refused to die. Allied intelligence counted the results. Thunderbolts averaged 7 times fewer engine failures than German fighters on comparable missions. In one documented case, a P-47 pilot flew more than 200 miles back to base with a piston cracked clean through, the engine still turning, still providing just enough power to get him home. The R-2800 didn't just provide power, it provided forgiveness. Act at Rechlin. Schultz's team received a new, desperate directive. Investigate turbocharger adaptation for German engines. It was a hopeless order. Germany's factories lacked the nickel to cast the turbine blades. They lacked the machining capacity to produce the delicate housings. Every attempt ended in catastrophic failure. An experimental turbo fitted to a BMW 801 melted into slag after just 15 minutes at full boost. Another shattered under the stress of uneven casting. The materials simply could not survive what the American Inconel alloys endured as routine. Desperation began to drive decision-making. If Germany couldn't build engines that lasted, it would build engines that burned brighter, if only for a moment. The Messerschmitt Me-262 jet became that obsession. It was fast, sleek, revolutionary, and catastrophically unreliable. The Jumo 004 jet engine that powered it was a work of genius born from absolute scarcity. Its turbine blades, which needed to withstand immense heat, were made from a material called chromodor. This alloy, a testament to German ingenuity, contained less than 5 pounds of chromium and no nickel at all, the very metal the R-2800 had in abundance. To compensate, the blades were hollow, allowing cooling air to be ducted through them. But it was an inefficient stopgap solution. The engines lasted, on average, only 10 to 25 flight hours before needing replacement. Pilots described the takeoff procedure as gambling with fire. One burst of throttle too fast, and the turbine blades would rip free, shredding the engine from within. Still, Berlin demanded production. The logic was seductive. If one machine could outfly the enemy, perhaps quantity wouldn't matter. But war does not honor perfection that cannot be produced. In contrast, the Americans built their imperfect machines by the thousands. A single plant in Evansville, Indiana, produced more P-47s in 1944 than Germany manufactured of all models of FW-190s combined. Each one carried the same R-2800, the same reliability, the same margin of survival. The Luftwaffe was bleeding to death in statistics it refused to read. In July 1944, Oberleutnant Schultz was invited to attend a technical conference in Augsburg, where senior engineers debated future priorities. The tone was defiant. "Our designs remain superior," one declared. "Their strength is waste. Ours is genius." Schultz listened quietly, then stood. The room fell silent. "Genius," he said, his voice carrying in the quiet hall. "Genius requires fuel." Everyone understood what he meant. The genius of German engineering had reached its limit. It could not feed the machines it built, nor protect them from the reality of scarcity. By autumn, Allied bombers were striking the refineries at Luna and Merseburg daily. Without high-octane fuel, the Luftwaffe's piston engines lost power, their superchargers starving for pressure. Meanwhile, the R-2800 roared over Europe on a steady diet of 100-octane gasoline, refined in Texas and shipped through convoys too numerous to stop. Every flight, every sortie, every escort mission was a demonstration of the same unromantic principle: logistics win wars. In one of his final reports before the war's end, Schultz wrote a single line that later historians would quote again and again. "They built engines for soldiers. We built them for engineers." It was both a confession and an epitaph. The R-2800 didn't defeat the Luftwaffe through innovation. It defeated it through its complete, absolute indifference to limitation. It was a machine that asked no favors and offered no fragility. In it lay the entire strategy of a nation that could afford to break things faster than its enemies could build them. When Berlin fell in May 1945, the surviving technical staff at Rechlin burned their notes, desperate to hide their work from the advancing Soviets. Schultz did not. He packed his sketches, his reports, and his alloy samples into a small case, believing that one day someone would need to remember what they had learned too late.
When American technical intelligence teams captured Rechlin, they found extensive documentation of the captured aircraft evaluation program. They found the flight reports from Hauptmann Hans-Werner Lurche, the test pilot who had flown Beetle. Lurche's conclusion was as sharp as Schultz's. Germany builds fighters for aces. America builds fighters for armies. And in total war, that difference is decisive. They also found Schultz's meticulous notes. An American engineer, fluent in German, sifted through the precise, handwritten observations on metallurgy and tolerances. In the margin of one page, he found a final, scribbled sentence, a thought that seemed to transcend the technical analysis. The engine is not what frightens me. What frightens me is how many of them they can build. That sentence summed up everything the Luftwaffe High Command had refused to understand. Power was no longer about horsepower or speed. It was about the ability to reproduce excellence endlessly. When the war ended, silence returned to the hangars at Rechlin. The test benches stood empty, the blueprints scattered across floors coated in dust and oil. The war that had consumed a generation was over, and the machine that had defined the German engineer's obsession, the American R-2800, had outlived the Reich that tried to study it. History rarely remembers the men who turn the wrenches. It remembers the pilots, the generals, the speeches shouted over radios, but not the quiet figures who bent over engines in dim workshops and tried to make sense of metal. Yet, it was in those workshops that the future was forged. Years later, General Adolf Galland, Germany's legendary inspector of fighter forces, confessed the error in their judgment at a 1985 reunion. "We made a terrible mistake in 1943, he said to a group of American and German veterans. "We saw this big, heavy fighter, the P-47, and we laughed. We were the ones who didn't understand. The Americans didn't try to build a European fighter. They built an American one, designed around production, firepower, and survivability. They understood that in a war of attrition, the plane that could take punishment and deliver devastating firepower would win. They were right." In 1962, a visitor to a museum in Washington, D.C. might have seen a restored Pratt Whitney R-2800 engine, standing silent beneath a polished glass dome. Immaculate, preserved, as if time itself had paused to honor it. A small brass plate read, "Engine from a P-47 Thunderbolt, 1944. A guide might explain to a group of schoolchildren how this engine had powered the fighters that won the air war over Europe. It was strong enough to take bullets, she might say proudly. It never quit. She would be right, but not in the way she meant. The engine's true strength was not in its horsepower or its armor. It was in the civilization that built it. A civilization that had understood that durability is mercy, that forgiveness forged in metal can save lives, that the simplest design made in great numbers will always outlast brilliance made in isolation. In his final report, Oberleutnant Hans Schultz had written one last damning conclusion. A conclusion that was not filed in Berlin, but was found by the Allies in the rubble of his office. A simple, four-word summary of the entire industrial war. We were outbuilt. The echo of that steel still speaks. It speaks through every factory that hums in the night, and every engineer who chooses reliability over pride. It reminds us that the machines we build are mirrors, and that progress, like mercy, comes not from brilliance, but from endurance.